Welcome to our Quantum Deep Dive. Today we're plunging headfirst into a subject that lives right at the really exhilarating intersection of two foundational realms of physics, quantum thermodynamics. We often call it QTD for short. It's essentially the study of heat and energy, but, scaled way down to the bizarre, counterintuitive quantum world. Our guide for this deep dive is an insightful essay by Jörg O. Schneepat titled Quantum Thermodynamic QTD Vermeleer de Quantenveld. Our mission today is basically to uncover how those classical concepts we think we understand, things like heat, work, entropy, get completely rewritten when we deal with particles that are, well, simultaneously here and there, or inexplicably linked across vast distances. And crucially, we'll connect this theory to why it absolutely matters for everything from building the next generation of quantum computers to even, maybe, understanding fundamental processes within biological systems. Think of this as your essential briefing, your shortcut to navigate this complex interdisciplinary field. It's packed with surprising facts and honestly profound implications. Okay, let's unpack this.
Yeah, and what's truly fascinating here, as you said, is the interdisciplinary nature. QTD isn't just some niche topic for, super specialized physicists. It's a critical bridge between two vastly different ways of understanding reality. On one side, you've got classical thermodynamics. That describes the macroscopic world we experience, steam engines, refrigerators, the laws governing thermal equilibrium, statistical averages. It's robust, fairly intuitive stuff. On the other side, there's quantum mechanics, operating at the atomic and subatomic level, where particles just behave in ways that defy our everyday intuition. So QTD is really about reconciling these two perspectives. And in that reconciliation, phenomena like quantum superposition, entanglement, and those constant quantum fluctuations, they aren't just theoretical curiosities. They become central to understanding how energy moves and transforms in these tiny systems. They fundamentally challenge and expand our very definitions of heat and work. It's quite profound, actually.
Okay, so let's cut right to it then. What exactly is quantum thermodynamics at its core? And how does it fundamentally break away from the classical thermodynamics that, maybe many of us remember from a college science course?
Well, at its essence, QTD is about taking those venerable classical thermodynamic concepts, things like work, heat, entropy, and extending them into systems that are undeniably governed by quantum mechanics. But it's far more than just shrinking down classical laws. It demands a really deep reevaluation of how these ideas function. The first radical departure is discrete energy levels. Classically, energy is like a ramp, right? A system can have any amount of energy continuously.
Right, smooth and gradual.
Exactly. But in the quantum world, energy is like a staircase. Particles can only exist in specific quantized energy states. They jump from one rung to another, never sort of hovering in between. This fundamental jump means heat transfer at the quantum level isn't about gradual warming, but about these distinct energy transitions. It completely changes the rules of the game.
So that whole idea of energy being continuous is just fundamentally wrong at the quantum level. It's all about these precise, distinct steps.
Precisely. And this leads us straight to the next big distinction: superposition and coherence. Imagine a quantum system existing in multiple states simultaneously, like a coin spinning in the air, showing both heads and tails until it lands, right?
Okay, yeah.
This coherence, this ability to be in a mixture of states, leads to entirely novel thermodynamic phenomena that simply have no classical counterpart. It's where, honestly, a lot of the quantum magic starts to happen. Then we have entanglement and non-locality. When particles are entangled, they're inextricably linked, no matter how far apart they are.
That's the really mind-bending part, isn't it? The idea of these invisible, instantaneous connections.
It is, and what happens to one instantly influences the other. These correlations profoundly influence how thermodynamic processes occur, often in ways that, well, completely defy our classical intuition about local interactions.
And I imagine at that tiny scale, things are anything but smooth and predictable.
You're absolutely right. The final key distinction is the heightened role of fluctuations on the microscopic level. Classical thermodynamics largely deals with macroscopic averages, where tiny fluctuations often just cancel each other out. We don't notice them. But in small quantum systems, these inherent quantum fluctuations become incredibly significant. They cause substantial deviations and make it a much noisier environment, thermodynamically speaking. They're not just background static. They're an integral part of the system's energy dynamics. Now, just as classical thermodynamics is deeply connected to statistical mechanics, using statistics to describe the collective behavior of countless particles, QTD connects to quantum statistics. And here we have to distinguish between Bose-Einstein statistics for bosons, Those are particles that like to clump together. They can even occupy the same quantum state, like in Bose-Einstein condensates. And Fermi-Dirac statistics for fermions. Fermions are the individualists. They adhere to the Pauli exclusion principle, basically. No two identical fermions can occupy the exact same quantum state. Understanding these different statistical behaviors is crucial, for instance, when you're designing things like quantum heat engines, because the type of particle fundamentally affects how energy is stored and transferred.
Ah, okay. And this is where the real-world implications start hitting home, isn't it? It sounds like these tiny quantum effects aren't just academic curiosities, but principles that could radically reshape future technology.
Absolutely. These are not abstract ideas floating around in theory. They are the bedrock for understanding and manipulating systems crucial for quantum computing, for designing molecular machines and nanotechnology, and for developing potentially highly efficient quantum heat engines and energy storage devices.
Right. To really get a handle on the significance of QTD, it probably helps to quickly look back at its lineage. Can you tell us a bit about the historical milestones that laid its foundation, connecting those two disparate worlds?
Sure. The story really begins, as you might expect, with classical thermodynamics. You have figures like Sadi Carnot, way back in 1824, analyzing the efficiency of steam engines, laying down the empirical groundwork. Then came the formalization of the first law, stating energy conservation, be it EU equals QW. Basically, energy can't be created or destroyed, only transformed from one form to another.
Energy in equals energy out, essentially.
Pretty much. And then the really crucial second law, which tells us that in a closed system, entropy, you can think of it as disorder, can only increase. That's captured by DSO0. Ludwig Boltzmann later gave us that incredibly profound statistical interpretation of entropy with his famous formula, SKB-BLNA. He connected the macroscopic concept of disorder to the number of possible microscopic arrangements, showing that entropy is fundamentally about probability.
So classical thermodynamics gave us the big picture of energy and disorder in the world we can see and touch. But then the quantum revolution started peeling back layers, didn't it?
Precisely. The early 20th century saw this explosive emergence of quantum mechanics. Max Planck, back in 1900, introduced the revolutionary idea of energy quanta to explain black-body radiation, this idea that energy comes in discrete packets, not continuous flows.
The birth of the quantum idea.
Exactly.
Yeah.
Then Albert Einstein, in 1905, extended this with his work on light quanta, photons, which really cemented the idea of quantized energy and also highlighted the fundamental role of quantum fluctuations. And then Erwin Schrödinger, in 1926, gave us the iconic Schrödinger equation, I(n euro S. This equation is, well, it's the mathematical blueprint describing how quantum states, represented by this thing called the wave function, evolve over time. It's deterministic, it shows the exact behavior of a single quantum particle, but it doesn't immediately tell us about heat or work in a statistical sense, like thermodynamics does.
Okay, so the big question became, how do you bridge that gap? How do you connect the statistical, ensemble-based world of thermodynamics with the precise wave function-based world of quantum mechanics? How do you merge those two views?
Well, that crucial step to bridge them formally really began in the 1930s with John von Neumann. He introduced what we now call von Neumann entropy, which is expressed as SVN equals TRLNO. Now, this isn't just a fancy formula. It's how we quantify the inherent uncertainty and disorder, or critically, the information content within a quantum system. It's the quantum mechanical analog to Boltzmann's classical entropy.
Okay, so what are the parts of that equation? Rho and tenor.
Right. So rho tau is the density matrix. Unlike a pure wave function, which describes a perfectly known quantum state, the density matrix describes a system when we only have probabilistic knowledge about its state. This is especially important when it's interacting with an environment, which is almost always the case in reality. And Tudor stands for trace. It's a mathematical operation that essentially sums up the diagonal elements of this matrix, boiling it down to a single meaningful value for the system's entropy. This was a critical conceptual leap. It laid the formal groundwork for QTD by giving us a way to actually talk about entropy in the quantum realm.
Okay, that makes sense. Now that we have that lineage, let's dive into the core concepts that really differentiate QTD. How do we redefine work and heat in a system that might be in multiple states at once? And what's the big deal about information in all this?
Right. That's where things get truly interesting, because those traditional definitions become quite fluid, mainly due to those quantum fluctuations we talked about. In QTD, we define the mean energy of a system as OIS, Tor. Remember, COP is the Hamiltonian You can think of it as the rule book or the total energy operator for a quantum system. It defines all its possible energy states and how it behaves.
Okay.
Now, when this mean energy changes, we can dissect those contributions. Quantum work is defined as dW equals Torr-def. This represents the change in energy that happens when you actively modify the system's rulebook. It's Hamiltonian. For instance, by applying an external force, like pushing a piston in some hypothetical quantum engine.
So you're changing the system itself.
Yeah, exactly. Conversely, quantum heat is defined as dQ equals 2 Torr-du. This is the change in energy that arises from modifying the system's state itself, its density matrix, usually through uncontrolled interaction with a thermal environment, like a bath of other particles bumping into it.
Okay, so work is about actively doing something to the system's intrinsic structure, its rules, and heat is more about the system's state changing through interaction with its surroundings. That distinction seems really crucial.
It absolutely is. And what's critical here is that because of quantum fluctuations, these aren't always deterministic values in tiny systems. They fluctuate. The Jarzynski equation, EWF, it beautifully demonstrates how non-equilibrium processes and fluctuations are not just noise, but are essential to understanding thermodynamics in small systems.
Okay, break that down a bit. Beta, delta F.
Right. So ABIS is simply 1 key dt, where Kb is Boltzmann's constant and T is temperature. It's basically inverse temperature. And EF is the change in free energy, which is the maximum amount of work you can theoretically extract from a system at constant temperature. This equation effectively generalizes the second law for small systems, showing that even far from equilibrium, there's a probabilistic relationship between the work done and the free energy change. It connects the microscopic fluctuations to macroscopic thermodynamic quantities. This also opens up fascinating discussions about the energetic limits for quantum machines. While classical engines are famously bound by the Carnot efficiency, APC equal 1 TCTH.
The ultimate speed limit for engines, right?
Kind of, yeah. But quantum machines might, in principle, exceed these classical limits by cleverly utilizing quantum coherence and entanglement as additional resources.
Whoa, hang on. Exceeding the Carnot limit, that sounds like heresy to a classical thermodynamicist. What's the catch there? It can't be a perpetual motion machine, so where does the information side come into play?
You're right to be skeptical. There's no free lunch, no perpetual motion. The core insight here is that these quantum machines aren't violating the second law. They're simply leveraging additional resources, quantum coherence and entanglement, that aren't accounted for in the standard classical Carnot framework. These quantum resources effectively allow for a more ordered or efficient energy transfer pathway.
Ah, okay. So it's using quantum properties as a kind of fuel supplement.
That's a decent analogy, yeah. And this brings us directly to the profound connection between quantum information and thermodynamics. That von Neumann entropy, SVN, TRN, rain row, it doesn't just describe disorder. It quantifies the information content, or lack thereof, of a quantum system. This link is central to revisiting thought experiments like Maxwell's demon, the little demon sorting fast and slow particles, seemingly violating the second law.
Right, creating order from chaos for free.
Well, in QTD, we understand that while measurement does reduce entropy in the system being observed, the demon gains information, the act of measurement itself isn't free. It requires energy, and ultimately, the processing and erasing of that information generates entropy elsewhere, balancing the books.
Ah, so the demon has to pay its energy bills after all. And this leads directly to Landauer's principle, doesn't it? That sounds important.
Exactly. This leads straight to Landauer's principle, which is really a cornerstone of information theory and its connection to physics. It states that deleting, or erasing, one bit of information fundamentally costs a minimum amount of energy. 1 min equals kBT ln2. This isn't just abstract theory. It's absolutely vital for designing reversible quantum computers. To minimize energy loss and heat generation during computation, you have to minimize information erasure. If you design your computation so it doesn't erase information, ideally it doesn't have to dissipate heat.
Fascinating. So computation itself has a fundamental energy cost tied to information.
Precisely. And one last point on core concepts. Time symmetry. While the fundamental Schrödinger equation describing a single quantum system is perfectly time reversible, the generalized second law of QTD, which looks at the change in von Neumann entropy, SO, shows that entropy still tends to increase in a closed quantum system undergoing some process. This gives a natural statistical arrow of time, even at the quantum scale, just like in the classical world.
Wow. Okay, this raises an important question. It really hammers home that it's not just about making components smaller. We're talking about fundamentally different rules governing how energy, work, and even information behave at the deepest levels. It really is a complete paradigm shift, isn't it?
It absolutely is a paradigm shift. We're moving from a macroscopic statistical view, where individual particle details often just average out, to a microscopic view where the unique probabilistic and interconnected behaviors of individual quantum entities, their coherence, their entanglement, their fluctuations, directly dictate energy flow and transformations. It's a much more nuanced and ultimately much more powerful way to understand efficiency and dynamics.
Okay, this all sounds incredibly theoretical, almost like science fiction in parts. But are scientists actually building and testing these quantum thermodynamic principles in labs today? What are the real-world implications playing out right now?
Oh, absolutely. This is a very bustling experimental field. Scientists are actively creating things like quantum heat machines, for instance. These are both conceptual models and increasingly real-world implementations based on multi-level quantum systems like atoms or artificial atoms operating between thermal reservoirs. They function much like classical Carnot or Otto cycles, but using a quantum working fluid.
So like building miniature engines with quantum particles as the pistons and fuel?
That's the idea, yeah.
Yeah.
You think of a quantum Otto cycle, for example. It might involve steps like isentropic expansion, where the quantum system cools while doing work but without exchanging heat, then isothermal heat absorption from a hot reservoir, then isentropic compression where work is done on it, heating it up, and finally, isothermal heat release into a cold reservoir.
And what are they building these with?
We've seen real-world implementations using cutting-edge technologies like superconducting qubits, the same kind used in many quantum computers, ion traps, which hold individual charged atoms, and optical resonators, which trap light. These systems act as the working substance of these tiny quantum engines. And what's genuinely exciting, as we touched on, is their potential efficiency. Some theoretical models and early experiments suggest they can potentially exceed classical Carnot limits.
And just to reiterate, that's not magic.
No magic. It's because these quantum machines can exploit quantum coherence, those superposition states, as a kind of resource, something classical thermodynamics doesn't account for. Coherence allows for potentially more ordered, efficient energy transfer pathways compared to a purely classical, disorganized system.
That's still a huge claim with massive implications for energy generation or cooling. But how on earth do you even measure things like quantum entropy or heat flow in these incredibly delicate, tiny systems? It sounds unbelievably challenging.
It is extremely challenging, you're right. Mainly because the density matrix, which fully describes the quantum state, including its probabilities and coherences, is difficult to access directly. You can't just look at it and read off the entropy. So researchers have to employ sophisticated methods. One is quantum tomography, where they perform many different types of measurements on identically prepared systems to statistically reconstruct the density matrix. Another way is by carefully measuring fluctuations in systems that are in the thermal equilibrium states and relating those fluctuations back to thermodynamic properties.
But surely these quantum effects are incredibly fragile.
Absolutely. A major nemesis for all these experiments is decoherence. This is where the quantum system interacts with its surrounding environment, inevitably, and those precious quantum properties, superposition, entanglement, get lost. The system starts to behave more classically. The timescale for this varies hugely. For example, superconducting qubits might lose coherence in microseconds. Ion traps can hold on to it for seconds, which is ages in the quantum world. And carefully isolated photonic systems can be almost immune to certain types of decoherence.
So keeping things cold and isolated is key.
Exactly. Cryogenics, cooling things down to near absolute zero, and building extremely well-isolated systems are absolutely crucial for observing and manipulating these quantum thermodynamic effects.
And are we also seeing these quantum fluctuations having measurable effects in, say, nanosystems that aren't quite full quantum engines?
Yes, definitely. There's a whole field called stochastic thermodynamics that specifically describes how these random thermal and quantum fluctuations modify thermodynamic laws in very small systems. We've observed these effects experimentally in things like nanomechanical resonators, tiny vibrating beams, quantum dots, semiconductor nanocrystals, and even molecular machines. For instance, the Jasinski theorem, that equation relating work fluctuations to free energy, has been elegantly demonstrated in experiments using optical traps to manipulate single molecules or particles. It shows these theoretical principles are truly observable in the real world.
Okay, and how does all this connect back to something more tangible, like the future of quantum computing? You mentioned that earlier.
Right, for quantum computing, QTD is absolutely critical for several reasons. First, energy efficiency. Thermal noise and decoherence caused by heat are major sources of errors in current quantum computers. Understanding quantum heat flow is essential for designing more stable, less error-prone qubits. Plus, cooling these machines, especially superconducting qubits, down to the necessary 1020 millikelvin that's colder than outer space, is incredibly energy-intensive. Better thermodynamic understanding could lead to more efficient cooling or designs that generate less heat in the first place.
And the information aspect.
Yes, entropy management is vital too. Landauer's principle, that fundamental energy cost of erasing information, directly guides the development of reversible quantum algorithms. The idea is, if your computation step doesn't erase information, it ideally doesn't need to dissipate energy as heat. This is key for scalability. But perhaps one of the most surprising and frankly mind-blowing areas where QTD might be relevant is in biological systems.
You mean like living things? The idea that biology itself might be using quantum thermodynamics? That sounds wild.
Precisely. It's a relatively new and incredibly exciting frontier, still debated, but with compelling hints. Consider molecular machines like ATP synthase, the protein complex that literally generates the energy currency of our cells, or motor proteins that walk along cellular tracks carrying cargo. They operate at the nanoscale in a warm, wet, noisy environment, yet are incredibly efficient. There's speculation and some modeling suggesting that quantum effects, maybe even coherence, might play a role in their function, potentially enhancing their efficiency beyond what classical physics would predict.
Wow. Any other examples?
Even more astonishing, perhaps, is photosynthesis. There's growing experimental and theoretical evidence suggesting that electronic superposition quantum coherence exists in the light-harvesting complexes of plants and some bacteria, like green sulfur bacteria. This coherence seems to help optimize the transport of energy captured from sunlight to the reaction center, where it's converted to chemical energy. It's almost like nature discovered quantum mechanics and quantum transport optimization long before we did, using it to be incredibly efficient at capturing light.
That is just incredible.
And there are even tantalizing hints, though much more speculative, that maybe some neural processes or the action of enzymes might leverage QTD principles for energy efficiency or faster reaction rate.
Okay, this is where it gets absolutely profound.
Yeah.
The idea that nature itself, in something as fundamental as photosynthesis, or maybe even how our cells work, might be using these subtle quantum tricks to be super efficient, that's truly astounding. It's like finding out life has been doing advanced quantum thermodynamics all along. So with all these discoveries and potential applications brewing, what does the future hold for quantum thermodynamics? What are the big theoretical puzzles still left to solve, and what's the really revolutionary potential it promises down the line?
Well, the future is incredibly exciting, but it's definitely rich with theoretical challenges. A huge one is trying to connect QTD with general relativity and quantum gravity. We need a theory that works for both thermodynamics and the fabric of space-time, especially in extreme conditions like black holes. We're not there yet. Another major challenge is developing a truly universal QTD framework that applies seamlessly to macroscopic systems, not just the tiny few particle systems where most current work is focused. How do these quantum rules scale up? And really getting a solid grasp on non-equilibrium quantum systems actively changing and exchanging energy, far from a stable state that's a very active and complex frontier.
So lots of deep physics questions still open. What about on the experimental side?
Experimentally, we've already hit significant milestones. The creation of those first proof-of-principle quantum heat machines in labs, and the observational evidence, like in photosynthesis, hinting at coherent energy transfer in biological systems. The future focus will likely be on scaling things up, building more complex quantum engines with multiple interacting qubits, improving their efficiency and power, and developing better measurement techniques for thermodynamic quantities at the quantum scale.
So it's about making these fascinating concepts more practical and, well, bigger in a sense.
Exactly. And the revolutionary applications are what truly drive a lot of this research. We're looking at the potential for genuinely energy-efficient quantum computers, which could dramatically reduce their cooling needs and improve performance by minimizing thermal losses. In nanotechnology, it could lead to things like quantum motors for incredibly precise medical applications inside the body, or new materials designed with thermodynamic properties controlled at the quantum level. And maybe, just maybe, entirely new energy concepts. Could we harness quantum fluctuations themselves, or use quantum effects to build radically more efficient solar cells or thermoelectric devices? These are longer-term visions, but QTD provides the theoretical framework to explore them.
Okay, if we connect this back to the bigger picture, QTD really isn't just some abstract theory tucked away in physics departments. It sounds like a roadmap that could potentially revolutionize how we compute, how we generate and use energy, and maybe even how we understand the fundamental processes of life itself. Looking at it from that broader perspective, what stands out most to you about its potential?
That's a great question. I think what stands out most is how it forces us to fundamentally reconsider the relationship between energy, information, and order at the most basic level. It suggests that the ultimate limits of efficiency might not be set just by classical laws, but by how cleverly we can harness these distinctly quantum phenomena, coherence, entanglement, fluctuations. It implies that information isn't just a passive bystander in physics, but an active thermodynamic resource. And that's a really profound shift in thinking.
I agree. What stands out to me is similar how it challenges our intuitions about efficiency. It's not just about optimizing existing processes based on 19th century rules, but about tapping into entirely new physical principles that operate differently. It suggests efficiency isn't solely about minimizing classical waste, but maybe about actively using the weirdness of quantum mechanics itself. The idea that there's still so much fundamental physics to uncover about something as seemingly basic as heat and work is truly captivating.
That's precisely it. QTD is a rapidly evolving field, forging this fundamental deep link between classical thermodynamics and quantum mechanics. It offers not just deep theoretical insights, but, as we've discussed, has profound implications across quantum computing, nanotechnology, quantum communication, and maybe even biophysics. And still many open questions, of course. How to fully apply these ideas to complex, non-equilibrium systems, understanding the complete role of quantum information as a thermodynamic resource, figuring out how it all scales up to macroscopic systems, and its ultimate connection, perhaps, to quantum gravity. These are the frontiers pushing our understanding of the universe. Maybe a final thought to leave you with. Consider how these insights into energy, information, and order at the quantum level might fundamentally reshape our understanding of efficiency, not just in the machines we build, but potentially in the very fabric of the universe, and perhaps even within life itself. It really encourages us to rethink what's truly possible.
Absolutely. It's a field that genuinely pushes the boundaries of our knowledge and opens up incredible, almost science fiction-like possibilities. Our exploration today was inspired by the insightful work of Yurgo Shnepat, whose essay provided a great foundation for our discussion on quantum thermodynamics. If you're eager to learn more about this fascinating world, you can delve deeper into quantum mechanics and thermodynamics by visiting schneppat.de. Thank you so much for joining us on this deep dive into quantum thermodynamics. Until next time, keep exploring, keep questioning, and keep being curious.